Good evening, everybody. Thanks very much for coming. I'm very impressed. It's nice to be back. Some of you may know that I spent pretty much all my childhood in Bath, and so I know Bristol fairly well, and I know Bristol's long tradition of interest in science. I used to come across here both to the university and to the annual lectures many times, so it's good to be back. Now, you had rather a long title for this talk just now. I decided that was too long and that I was going to call it Thriller. And the reason for that will emerge as the talk progresses. But really, this is a story, very interesting story. I think it's the most interesting story, arguably, in human history. And you'll see why that's the case as the lecture unfolds. So, I'm a physicist by training, and physicists are trained to look at the world in a particular way and try and find underlying principles and laws that it behaves. So it's a way of making sense of it that has proved very helpful. It's allowed us to put man on the moon and so on. And some of you may have come across Samuel Butler, who's a British thinker, philosopher, writer from the 19th century. And I came across an interesting quote, which I've slightly paraphrased. I think I've improved it, but you can decide, you can look it up. But he made this comment: all progress derives from the ineluctable desire of every organism to live beyond its means. Now, if you're a bank manager or a parent, you kind of instantly recognize that there is some truth in this. But in terms of organisms that have been successful in shaping the world to suit their needs, we, humanity, are arguably the most powerful example. So our progress has derived from our ineluctable desire to improve our welfare, improve our well-being, and arguably this has led us, in many cases, to live beyond our means. So that's a sort of starting underlying principle for this story. So we all enjoy the modern world. I mean, there are over 7 billion of us. It's easy to forget that 1.5 billion don't have access to electricity and are going to bed hungry tonight. But for those of us that don't fall into that category, we're living a quality of life which is pretty much unmatched in the history of humanity. A few very privileged people have led lives of this quality, but we're privileged to do so. So how has that come about? Well, there are a number of factors, and I've sort of listed some of them here in the order that's kind of interested me. First of all, science. We've found a way of making sense of the world where we do find underlying principles that seem to be basic truths, which we then exploit through our ingenuity in our technology, in the way we organize ourselves and so on, which are one of the key factors in the modern world that we enjoy. Now, that ingenuity needs to turn things into reality, and it requires some sort of funding, some means of persuading other people to participate in a cooperative exercise to deliver the goods and services and products and so on that we enjoy. And there have been many ways tried to fund that, but whatever you think of it, and some are pro and some are less pro, capitalism has proved to be a very powerful way of making progress in taking advantage of science and ingenuity, and more recently, the globalization of the world economy has helped too. It's really strange. My wife went to Specsavers about a year ago to collect her new spectacles, and they said, sorry madam, they're not ready, the lab's been flooded. And she said, but we're in a drought. And they said, not in Thailand. Thailand is flooded at present, and when the lab is running again, you'll get your specs. One of the other really important underlying factors in literally powering the building and running of the modern world has been our access to this El Dorado of fossil fuel energy that was stored up by biological and geological processes over hundreds of millions of years and left enticingly just below the surface of the land or ocean, relatively accessible, beautifully usable, incredibly intense. And that access to relatively cheap usable energy has literally powered the modern world. We know that any interruption in that fuel supply leaves us very vulnerable. Some of you may remember that, 150 tanker drivers who distribute the liquid Petroleum around the UK went on strike in September 2001, was it? And the time constant for society to get into trouble was about a week. In about a week, we were all on the verge of starving because Tesco's and Sainsbury's were empty, and the government was meeting, worrying about civil unrest, and so they sorted out the delivery, and when it was reinstated, here we all were. But how long would we survive without that supply of energy, whether we like it or not? And then the other factor is an unusually stable climate. It just turns out over the last 5,000–6,000 years ago, the climate system has been extraordinarily stable compared with what we know it can do, what we know from paleoscience it's capable of doing. And many people have argued that that allowed agriculture and civilization and the modern world to develop in that stable period. So, here's an example of the result of those factors combining and human effort. This is Doha, where world leaders who are worried about the climate system and what it might be doing, and those who are worried about the economic system, have all met recently. And this is a clearly human-constructed environment. That environment could not function without the economy, without the fuel supply, without the modern technology, and so on. So arguably that's a fairly brittle environment which we enjoy, and that it wouldn't take much to disrupt its functioning. So maybe in that respect we are living dangerously close to our means. And a group of scientists thinking about this more generally came up with a publication a couple of years ago in this very prestigious journal called Nature, where they looked at planetary boundaries. And so this diagram shows the planet symbolically, and there are 9 sectors where they said, let's have a look at the intersection between this modern world, humanity, and the environment, the planet, our life support system. And let's look at it through various lenses. Let's look at it through the lens of climate change. Let's look at it through the lens of water use, land use, the disruption of biogeochemical cycles, because we use so much nitrogen in our fertilizers, we disrupted the phosphorus cycle and so on. Look at the changes that we've made in habitat by terraforming more than half of the land surface of the planet for agriculture, the impact that that's had on biodiversity, the pollutants that we push out into the atmosphere, and so on. So they had a look at these 9 sectors and said, are we running close to the limits? Are we living beyond our means in any of these areas? And the areas marked in orange show the ones that they feel that they're concerned about. In the one case, in terms of biodiversity loss, we're seeing a massive extinction event going on. So their argument was very plausibly that we're living way beyond what would be a sensible boundary there. In terms of the disruption of the nitrogen cycle and the consequences of that, we've gone beyond what would have been a prudent boundary. And on climate change, the one that points up to the top, we're kind of at the boundary. We're kind of pushing the limits. And the references there. It's an interesting paper, and it's a nice way of looking at the interaction of this fossil fuel-powered modern world and the environment. So here's a picture of the planet. A nice picture, one of 2 taken by the Apollo astronauts, Apollo 17, so the last mission that went to the moon. In those days, they used cameras with film. There'll be a lot of people here who've never seen a camera with film, but a lot who remember it. And you remember that when you were going on your holidays, you tended to keep the pictures, because you'd only got so much film to take pictures of your destination. So they'd been told to take pictures of the moon, not of the Earth, but luckily they took 2 of these pictures. They're very nice because they're the only ones with the sun behind the photographer, so you have a fully illuminated disk of the planet. And for me, somebody interested in the Antarctic, you can just about make out the Antarctic at the bottom. So there's a lot one could say about this object, but I've called it the most complex object, and I'd just like to point out that it is the only object that we know of, because of that green stain across Africa there. It's the only one that we know of that's got biology on it, so it's got physics, chemistry, geology, it's got biology. But the fact that the photograph exists, it also indicates it's got a very special form of biology, that is us, an organism capable of projecting one of its members or a few of its members up there who could take the photograph. So my argument is that this is the most complex object in the universe that we know of. It may well be that there are others out there, but we have no definitive evidence of that. And I'm interested in how complex objects work. it's also quite important to understand how this object works because it is our life support system. It provides the fresh air, the fresh water, the food, the fibre, and so on and so on. It is our space capsule. So damaging that life support system is probably not a very wise thing to do, and so we have to decide whether that's a limit that we might be reaching. Now, the way that scientists work is they take a complex object like that and they say, well, we can't understand the whole thing, let's start to tear it apart and we'll look at the little pieces of it. And so here's a very high-level diagram, which already looks hugely complex, of some of the pieces of that Earth system and how they're connected and how they interact. And I'm not going to test you on it afterwards, but I just say that on the left-hand side you have the influence of the sun. After all, the energy that drives this system, the motions of the fluids, the motions of the ocean, the motions of the atmosphere, the rainfall, the waxing and waning of ice sheets and so on. All of that energy is flowing in from the sun, it's borrowed, it's used for a while, and then it's radiated off into space, and the planet is in some sort of a close balance. And of course that energy also drives photosynthesis, upon which all of us rely. So the variations in the output of the sun have an influence on how this machinery works, as do the impact of volcanoes, because they push aerosols up into the upper atmosphere and they reflect away some of that incoming energy from the sun. So there are at least two influences on the way this whole climate system functions. There's a lot of internal variability, things interacting with each other. But on the right-hand side, we've got what I've just called human activities, which are to do with the chemicals that we put in the atmosphere, the way that we change the land surface and so on. And so you can draw another diagram here which shows other impacts on this system which all interact with each other and in the end have consequences for human activities, in this case climate change. So one of the prime ways that humanity has had a measurable impact on the planet is by burning that fossil fuel to get energy from it. But unwittingly, the energy was just the transient byproduct. The real product was the carbon dioxide that we got when we burn the fuel. We do it all the time. And of course, if you just take a kilogram of carbon and you burn it, it combines with oxygen from the air and you get 3.7 kilograms of gas, which diffuses out into the atmosphere. So if you all take a big breath, you're breathing a lot more carbon dioxide now than your great-grandparents were, and probably your grandparents. And this diagram illustrates it. I'm not going to show you terribly many graphs, but this is a diagram that shows the time profile of carbon dioxide in the atmosphere over the last 500,000 years. And it's derived from little bubbles of gas which have been trapped very conveniently by Antarctic ice. So the snow fell, it trapped bubbles of ice, more snow fell on top of it. And if you drill down through the ice, you go back in time and you can release the air from these bubbles over that long period of time and measure what the carbon dioxide content was. And the story that you can see is that there's a lot of wobbling around, noise on the signal, but basically you've got four kind of sawtooth profiles here, which are the four last ice age interglacial cycles. So you start at a warm period at the top, you make your way down into an ice age, you jump back out of it, you make your way down into the next ice age, you jump back out of it, and so on. And then on the right, you jump back out, and we're in the present period, which geologists call the Holocene. I've drawn two dotted lines which show that the system has a couple of natural limits that it tends to stabilize at. So in the warm period, there are about 280 units of carbon dioxide in the atmosphere, and in the cold period, there are about 180 units. Well, if we just add what's happened in the last 100 years, we get the red line here, so we just go now. So by burning half a trillion tons of carbon in the form of coal, gas and oil in the last 100 years to construct and operate the modern world, which we've just released into the atmosphere, unwittingly thinking that was fine, it's a big atmosphere after all. It turns out that we've increased the carbon dioxide content of the atmosphere by the same amount as the system naturally wanders between on these ice age cycles. Now, those ice age cycles take about 100,000 years, 110,000 years. And we've done this in 100 years, or less than 100 years. So we've done it 100 times faster than anything that you can find in the natural record. And it's the same amount as the change between an ice age and an interglacial. And we know that between an ice age and an interglacial, the average temperature of the planet changes by about 5 degrees, and at the polar regions you get an amplification, it's maybe about 10 degrees. So the question before and of course that complicated system, all interconnected, is responding to this. It's like a shock in the system. You know, it's if you take a musical instrument and struck it, and the consequences are still working their way through that system. So this is the carbon dioxide. This is measures, no models or anything associated with this. We know that that's happened. We know that carbon dioxide is a greenhouse gas. We know that the greenhouse gases keep the surface of the planet about 25, 30 degrees warmer than it would be if they weren't there. So we can expect a temperature response. So what we've done is we've introduced an energy imbalance by increasing the carbon dioxide in the atmosphere, by the way, into a regime that the planet hasn't visited, hasn't experienced. We know by measurement for 850,000 years, but we deduce from other proxies for probably about 30 million years. So we're in a regime that the planet hasn't visited for a while, certainly not in human history. We've changed the energy balance of the planet. So we've got energy coming in from the sun, we've increased the greenhouse blanket, if you like, so slightly less energy is being radiated back out into space, and that means that energy is being accumulated by the planet. And this little wobbly curve shows the best estimate that we've got at present of that net balance. So you see that it wobbles about all over the place. You know, the planet is constantly reacting, doing things, doing what it does. Clouds come and go. The tropical oceans, you know, go through ENSO cycles and what have you. But the net has been an accumulation of energy because there is slightly less going out than there is coming in, on average. Now, where does that go? Well, anybody who knows the first law of thermodynamics knows that energy can neither be created nor destroyed, but it can be changed from one form to another. So energy that's come in as light and heat can be converted into warming of ocean or land, can be converted into biological molecules. That's what the photosynthesis does. It can melt ice, it can evaporate water, it can disappear down into the deep ocean. It can go into all sorts of places. And part of it, of what's going on, is revealed by the surface temperature data set. But that's not the whole story. The surface temperature data set just gives us one insight into where some of that energy is going. But because the oceans are dark, and much darker than the land, and because they cover 70% of the surface of the planet, about 90% of that energy imbalance is going into the ocean. So if we want to check that our theory, if you like, our hypothesis that the Earth is accumulating energy is right, then the place we should go and look for it is in the ocean. Is there evidence that the ocean is accumulating energy? And the answer is yes, there is evidence, because we can measure how much the ocean is rising. Now, we know that once we'd come out of the last ice age, 10,000 years ago, where there had been a massive change in sea level as the ice sheets melted back, 120 meters of sea level change, that things have been fairly stable, certainly for the last few thousand years. Not a lot going on, more or less stabilized. But over the last 100 years, we've seen sea level pick up and begin to increase. And I've called it the planetary thermometer. You all know how a thermometer works. If you have a bulb of liquid, it could be alcohol or it could be mercury, and you have a tube which you can calibrate. If you warm up or cool down the liquid, the thread of liquid will either expand up the tube or decline down it, and you can calibrate it and measure temperature. Well, in this case, the planetary thermometer has the liquid held on the planet by gravity. That's the ocean being held on there. And if you warm it up, it expands. If you melt ice on land, the water goes into the ocean, and that also causes the sea level to rise. And there are various ways that we can deduce what sea level rise has been doing for this last 100 years. Most of the older data set over the last century has been derived from tide gauges. Tide gauges were put in because people were interested in, naval nations, fishing nations, interested in looking at sea level, measuring tides, knowing when to get fleets in and out. And so those data have been appropriated and used to derive a sea level curve. And we can see that sea level has been rising. The little black line towards the end is derived from satellite instruments that constantly orbit the Earth, firing radar pulses down to the surface of the ocean and give us a measure of global mean sea level on roughly a single figure every 10 days. So this is like a thermometer showing that the ocean is both warming and accumulating more water from the melting of ice on land. And it turns out that there are satellites that measure the gravity of the planet so accurately that they can distinguish what proportion of this rise is due to additional water having gone into the ocean, increasing its mass, and what proportion is due to thermal expansion. So anyway, we have a measure that the planet is warming. So if there's one, Jim Lovelock uses this as his only view graph to say, if we want evidence that the planet is warming, this is fine, this does it for you, this is unarguable. Now, one thing that's important to note is that the sea level doesn't rise uniformly over the whole planet. There's all sorts of complex processes going on, currents, we've taken out the tidal stuff, but there are reasons why you get different rates of rise in different parts of the ocean. What we were looking there on that previous curve was a global mean figure. But it does mean that you could go to some part of the planet and say, well, wait a minute, the sea level's going down here. But that doesn't invalidate the argument that I've just made, that on average, the ocean is accumulating energy and water as demonstrated by that curve. Now, the reason that I said that is that it's important to recognize in climate science that if somebody says, what is the one single piece of evidence that convinces you that the world is warming and that it's due to human beings, that is an unfair question. It may be that a detective investigating some crime catches the individual red-handed, and so that would be the one bit of evidence. But usually in trying to understand what has happened, you have to put together lots of pieces of evidence, weigh them up, and there will often be counter-prevailing pieces of evidence that doesn't fit. And sort of illustrate that with this little animation. If I scatter iron filings onto a sheet of paper and we end up with this pattern, I would hope that everybody in the audience would say, aha, well, those iron filings are tracing out the magnetic field lines, and that underneath that piece of paper we can be pretty certain that there is a bar magnet. Now, if you hadn't seen me scatter the iron filings, I could have got a sushi chef in, and they could have painstakingly placed all the iron filings in that pattern, and there might not be a bar magnet underneath, but if you've seen them go down, then probably there is a bar magnet there. If we zoom in onto any one of those iron filings, you may find that it's been stuck on the paper, maybe it's magnetized across its length rather than along it. You will find little pieces of evidence that suggest that there isn't a bar magnet under there. But what you do is you look at the overall pattern. And this is the case with climate science. We look at all the different evidence drawn from a multitude of different studies and weigh them up. And we will always find some bits of the ocean that are going down when the average is going up, some bits of the planet that are cooling when the average is going up, and so on. And a lot of the confusion about climate science is because individuals find some piece of evidence that seems to contradict the general view, and they essentially cherry-pick those and focus on those, when in fact what one has to do is take a balanced view of all of the evidence. Now, you still have to explain why that piece of evidence is either mistaken or explicable, but it doesn't necessarily undermine the entire picture that you built up. So I'm not going to go through all of the evidence because I'm a bit concerned about time, but I just draw your attention to a couple of things. One of the things that the science community said 20, 30 years ago was that they predicted that there would be an amplification of any warming as a result of the greenhouse effect, which I've just shown you, in the polar regions. And to their surprise, the Arctic has responded far more strongly to the warming, and it is warming more strongly than they predicted. And it was interesting, I was asked recently to chair a discussion following a showing of Al Gore's Inconvenient Truth 6 years after it was originally filmed. And one of the things that struck home really hard to me was that, there was Al Gore, looking a bit thinner than he does now. I'm sure he wouldn't mind me saying that because it's true. But at one point he said, and in the Arctic, the science community is predicting that within 50 to 70 years, we might see very strong reductions of the Arctic sea ice, maybe an ice-free Arctic at the maximum summer meltback. And in 5 years, that prediction has changed to 10 to 20 years. And in fact, if you look at the curve, the picture on the right is looking down on the Arctic Ocean, which you remember is the exact mirror image of the Antarctic. The Arctic is an ocean surrounded by land, which in the winter freezes up, the surface freezes up. and some ice is left in the summer. And the Antarctic is the opposite continent with a big lump of ice on it and ocean all the way around it. So we're looking at the Arctic here, and the orange line shows where summer sea ice extended to at maximum meltback just a few decades ago, and then the white shows where it was last year, and then the dotted line graph on the right is the volume of that floating ice, which shows a very dramatic decline. And in fact, the bottom of this graph shows 0, an ice-free ocean. And it is not what I am predicting, but if you just draw the dotted line, it actually goes through 0 in a few years' time, 2015, 2017. Now, scientists are very conservative, and even the most extreme is not saying that we will see an ice-free Arctic in 2017, although who knows. But nevertheless, the estimates of when this very dramatic new state of the Arctic will be observed have reduced very substantially over the period of 5 or 6 years since Inconvenient Truth was put together. And this is a bit complicated, but I'm going to try and explain you through it because I think it's rather nice. This is a kind of death spiral image. What it shows is year by year, starting with 1979 at the top and working around like a clock to 2013, where we are now, coming up to sort of 11:30. And what it shows is year by year, the annual cycle of ice growth and decay, the sea ice volume growth and decay. So maximum is in this sort of April, May, at the end of winter, and those are the green curves, and you see them on the outside, because that's the maximum volume. And the minimum volume is in September, that's maximum ice melt, and that's the black curve in the middle. What this diagram shows is that the succession of growth and meltback cycles since 1979 have followed a progression to the point now where the winter maximum volume is what the summer minimum volume was in 1979. So when you hear people say, as has been in the newspapers recently, oh, it doesn't matter, the Arctic meltback this winter has been the strongest ever, it's all going back to where it is, that is not true. If you've had a maximum meltback in the summer, it's not surprising that when it gets dark and cold up there, the surface of the ocean freezes over, but it's very thin ice, and it doesn't extend to where it used to. So we're seeing a very dramatic and unusual change in the Arctic. That's the Arctic sea ice. If we look at Greenland, which in some ways is of more of a concern, because it's the ice on land that melts and pours into the sea that causes sea level rise, which you can see has consequences. If we look at Greenland, the image on the left shows in colour the accumulated number of days throughout the year that the surface was melting. So where you get light colours and blues, only a few days in the year would you see melting on the surface. Where you get reds and very dark colours, you get rather a large number of days, 90 or 100 days. So over the period 1979 to 2007, a typical year, an average year, would be as in the left panel. That is, you would get quite a lot of melting around the lower periphery, particularly in the south, but virtually no melting on the high dome of the Greenland ice sheet. And then on the right, you see what happened last year, where some melting occurred everywhere over the ice sheet, even for a short time. This is a very dramatic change. And when people say, well, there are cycles and things like this that have happened in the past, this is very unusual stuff. And I mentioned that civilization had prospered during an unusually stable climate. And I hope you can see what this curve shows is temperature data derived from a Greenland ice core, which show that during the sort of last phases of the last ice age, there were very substantial climate flickerings. Can you see these temperature spikes in the curve there? Where to the resolution of the ice core, which maybe, I don't know, it's less than 10 years, 7 years, the climate over Greenland and from other data over the North Atlantic and Western Europe would flicker. So it would change 10 degrees in a few years, sit there for 10, 20, 100 years, and then flicker back again. Now, during the rise of civilization, the last 5,000, 10,000 years, things have been much more sedate. There's been a little wobble, there's been a slight decline. And we know that the medieval warming and then the subsequent Little Ice Age had big impacts on humanity, even at those small levels. But we ain't seen nothing. What humanity has experienced is an extremely benign climate system. And what we know that, at least in the cold state, it's capable of is much more rapid and violent change. Now, in the warm state, we've gone off into this unexplored area, or area unexplored by the planet. So we don't know if these rapid change mechanisms could kick in or not. But that's the point. We don't know. And we have to consider that risk. Now, the reason that all of this is important is because even with the climate system that we inherited and that we constructed the modern world to cope with, our agriculture, our water supplies, our railway lines, I had a very uncomfortable journey the other day, being thrown around on a very fast train, and the guard said, well, it's because it's so cold, all of the railway lines have sort of shrunk and buckled. And you go, well, yeah, that's right. I mean, it hasn't been much of a change, has it? But basically, we're imperfectly adapted to the climate system that we inherited, and we see that all the time. So it's probably not wise to take the risk of provoking that climate system to behave more erratically. So what is the problem? Well, if we do, we have to consider availability of water. Remember that we're 7 billion people now, 9 billion people predicted by 2050. Question, are we living beyond our means? Will we be living beyond our means if we disrupt this life support system, an important component of which is a stable climate? So there's availability of water, productivity of farms, forests and fisheries, the geography of human and animal diseases, the prevalence of oppressive heat and humidity. I'm not going to show it because I don't have time, but there's an amazing curve that shows how much work a human being can do in a very hot, humid climate. The amount of work you can do falls off enormously. So unless you have an engineered environment to protect you from very hot, humid weather, human productivity fades off very rapidly. Question of extreme weather, running costs of these engineered environments, damages due to sea level rise, and so on. So there are lots of issues here. And the medical community kind of woke up to the consequences of climate change a year or so ago, published a very interesting series of insightful reviews in The Lancet, looking at the health impacts of climate change, which are non-trivial. And of course, the stakes get even higher. Even the Daily Mail was moved to publish this result, which some of you may have caught last week, which was a bit surprising and not very comforting, that evidence from stalactites in a Siberian cave show that they, of course, only grow when liquid water is seeping down through the roof of the cave, and that this only happens when there is liquid water. They're in a permafrost zone, so most of the time there is no liquid water. It's frozen into the ground. What they found was evidence that it only takes 1.5 degrees to change permafrost to liquid water, and that if the climate overall changed by 2 degrees, which is, remember, what governments are committed to, there would be an amplification in the polar regions, the permafrost would melt, and there is a huge store of carbon which would be released in the form of carbon and carbon dioxide. So there's the potential for some sort of runaway greenhouse effect and climate change there, which we would live to really regret. So I don't want to be alarmist, but there are big things at stake here, and who knows whether that's right or not, but it's a warning. So the bottom line is that the science community, the climate science community, has concluded the following, that it's real, that the climate is changing. Now, of course, that might be for lots of reasons, but they have evidence, we have evidence, that the main driver this time, not the only driver, but the main driver is us and our the unwitting consequences of burning all of this carbon from which we've all benefited. And that there is evidence that this is problematical. I mean, forget the melting of the permafrost, just look at the other consequences. So we should really be taking this seriously. And again, Jim Lovelock says, he said, it's as if we're sleepwalking. He said, I remember, he says, what it was like in the 1930s when the lone voice of Winston Churchill was saying, I think we really might have a bit of a problem brewing in Europe. And nobody really wanted to hear that message. So the phony war developed, and that lone voice was saying things like, we're getting to the point where we need to do something. The era of procrastination of half measures, of soothing and baffling expedients, of delays is coming to its close. In its place, we are entering a period of consequences, from which you learn two things. Politicians could write and speak really rather well in those days. I hear that in the recent by-election words quite like that. But secondly, that a lone voice may still be speaking the truth, even if everybody else prefers not to listen. So what this suggests is that we need to take collective action. We're perfectly capable of taking collective action, and it requires a collaboration between business, government, and people. Now, actually, it's the bottom left-hand corner that's really critical in this, because it's the businesses of the world. It's the Coca-Colas, it's the Apples, it's the Tesco's, it's the Marks and Spencers, it's the Toyotas, who are planning now the goods and services that you and I will consume in 10, 20 years' time. So they are shaping the future that we will experience. And interestingly, a lot of those businesses have really got it. They use a risk-based approach. They say, well, wait a minute, we're already sensing some vulnerability in our supply lines. My wife's spectacles, this is disruptive. We're seeing some sensitivity, some vulnerability to the climate that we inherited, regardless of whether we've changed it. So maybe it'd be wise to invest in making ourselves more resilient so that we have a better business model. We can be more confident about the profits that we'll make by addressing the climate system that we have, and then thinking forward, looking forward at what the projections say, and seeing if there are ways that we can invest sensibly to make ourselves more resilient in the future. Now, in order to do that and at the same time remain competitive, if other people aren't doing that and there are costs involved, then it's helpful if governments make agreements, both nationally and internationally, to ensure that everybody else adopts the same standards and follows the same sorts of practices. And then governments find it difficult to do this if they don't have support from the people, at least in democratic societies. So it's a collaboration between, a coordination between those three subsets of society. Of course, people form business and form government as well, so that distinction is slightly false. But unfortunately, it requires that to be done globally. A very powerful argument is, well, what's the point of the UK sorting out its carbon emissions if nobody else in the world does? We just emasculate ourselves. So it requires a level of coordination which is unprecedented and not easy. It's often said, but, well, nothing is being done, and that is just simply not true. A huge amount is being done. Now, of course, the United Nations process has been slow and painful, but if it hadn't existed, many other things would not have happened that have happened. The mayors of the 40 large cities have, introduced many initiatives using the United Nations framework as their, if you like, their top cover, their framework. And the figure of 2 degrees and what that implies in terms of reducing carbon emissions, which has emerged from the United Nations process, has been a sort of standard that everybody has adopted, rightly or wrongly. And the centre little diagram there with the black footprints shows that individuals too can map out their carbon emissions and take actions to reduce them. And actually it turns out that if you do that, it's quite easy to reduce your carbon emissions quite a lot. And why shouldn't you? It saves you money usually. Makes you feel a good citizen, good example, and so on. So an awful lot has been done. But it has been overwhelmed by the growth in the rest of the world where people who are willing to work very hard to aspire to and achieve the quality of life that we enjoy are doing just that in a fossil fuel carbon-intensive way and have, if you like, overwhelmed the efforts of others to reduce overall carbon emissions. So unfortunately, the curve of carbon emissions has continued to accelerate rather than to turn over and reduce. It's perfectly understandable and actually difficult to challenge ethically. So scientists, as we'll see in a minute, are often accused of being alarmists, but actually they're alarmed. They're alarmed at the rate that this ineluctable rise of living beyond our means seems to be progressing, and the fact that the level of traction we have on trying to live within our means is so puny compared with what is actually required. So, of course, thoughts turn to adaptation, and the kind of iconic bit of adaptation in London is the Thames Barrier, which you can see in this quite nice image. I like this image because it really brings home to you, doesn't it, the extent to which London is at risk of flooding. You know, taken from this angle with that huge estuary, you know, with the right tide and the right wind set and the right amount of water coming down. You know, it only takes one overspilling of the embankment to cripple London. So adaptation is certainly something that we have to address, because it's clear that we are not going to be able to manage down our carbon emissions in the way that it would be necessary to retain the climate system that we inherited. We've lost that opportunity. But there are limits to adaptation. And when people say, let's just sit back and adapt, I'm sorry, there are limits to it. You know, if the vast area of agricultural land becomes unusable, that is really serious. There's not much you can do about it, not unless you invest enormous amounts of energy, which make the situation worse. So there are limits to how much we can adapt. So what's going on here? You would think, wouldn't you, that faced with this quite disquieting evidence, that there would be a lot more public discussion and a lot more engagement of everybody to try and figure out what can we do about this. You know, it's unlikely that we're going to be able to solve the problem perfectly, but surely we can do better than we are. So one of the kind of privileges that I've had in the last couple of years at UCL is to be able to invest time and effort looking into things that I've not studied before. And so I've been looking into this thing. And I've come to the conclusion that for 30 years I've probably been studying the wrong complex object. This complex object is not only really interesting and fascinating, but it's a key barrier in addressing that question that I asked just now. You know, well, why is it that we're not more engaged in trying to address this problem? So the first thing to understand is that climate science is a bit different from what you might call traditional science, traditional physics. So I'd call it not the Higgs. It's not the Higgs boson. If I were to give you a talk this evening about the Higgs boson, depending on how good I was, I could inspire, enthrall, interest you, engage you in a fascinating story about uncovering the mysteries of the universe. And at the end of the evening, in half an hour, you would walk back out of those doors and your lives would be materially unchanged. But climate science isn't like that. I've told you this story. I could ask you, how are you feeling? You're probably not feeling wonderful. You're probably feeling anxious, worried, upset, angry. Ask yourself how you're feeling. You're feeling different than if I'd been telling you about black holes or particles or the Higgs boson. And you're reacting. You're reacting with anxiety, fear, grief, guilt, anger, all of the things unconsciously or consciously that the human brain does. There's a lot of interesting thinking going on about how we make sense of the world at present, and a lot of popular books which I can recommend. And what they show is that we react to the world around us emotionally, unconsciously, and that causes us to react to the information that's coming into us. And the conscious part of our brain, the brain that does the careful evaluation of facts, or tries to, is quite slow in comparison and kind of kicks in. It's fairly lazy too, and it kind of kicks in when it feels that it needs to. And that's really important because, as I was saying to some people earlier today, if suddenly somebody ran at me from the right-hand side of the platform and threw something at me, my conscious brain wouldn't try and fit a quadratic equation to the missile and figure out whether it was going to hit me or not. My amygdala would send a surge of emotion into my brain and I would duck completely unconsciously without thinking about it. And that's actually how we process most stuff. So whilst I've been telling you this disquieting story, I have been generating it within you: anxiety, fear, grief, guilt, anger, probably a sense of helplessness and so on. Now, that picture illustrates how we react to those feelings. We don't like it, and we have all sorts of mechanisms to deal with those discomforting feelings. How do we react? Defenses are raised. We try and suppress those feelings. We don't like them. We provide arguments to justify why Chris is wrong. How many of you have been thinking, I don't know whether I accept that evidence or not, because you don't want to, because it's not very nice evidence. Al Gore's choice of the words inconvenient truth were very careful. This is not a message that any of us like very much. It's not a message that I like very much. Nobody would be happier if we woke up, all of us, tomorrow morning and discovered that this was all a bad dream and that we could go on burning fossil fuels with impunity. Unfortunately, the message is uncomfortable. And what happens is that we seek ways to justify rejecting it. Often a common response is anger. I don't like you making me feel unhappy. You are making me angry. I didn't come out on my Friday night to have my evening spoiled. I wanted to listen to an enjoyable talk, and you just ruined my evening. So the messenger is often blamed. And where does that lead us? It leads us to various stages of dealing with this. We have these mechanisms to deal with unwanted and unwelcome news. We either dismiss it and say, I don't believe you. I just don't believe that humanity could be doing this. We're too small, we're too puny, you got it wrong, the greenhouse effect doesn't work like that, something will kick in, it'll be fine, go away please, I want to listen to something more entertaining. Or another phase is disavowal, where you go, okay, well it probably is right, and I'll believe it in this bit of my brain, but wait a minute, I've got to go and pick up the kids, and I'm going to Tesco's, and where was I flying tomorrow? Oh yes, I've got to go and do that. So it's disavowal, where you know and you don't know. And actually, climate scientists are probably the most perfect example of people who are in deep disavowal, because we know better than anybody what's at stake here, and yet we go on leading our lives, because we have to. And we have to have a mechanism where we separate what we know from what we do. And then there's discounting, where you say, well, okay, I accept it, the climate is changing, it is us, probably is something we can do about it, but actually, maybe it won't be so bad, maybe something will happen. You find some way of justifying not actually taking those actions which the evidence suggests that you should be doing. So there we all are, we've got this uncomfortable knowledge, we don't like it very much, and somebody on the side is saying, psst, science is very uncertain. And we go, oh, is it? Oh, thank goodness. Well, that's great. Yeah, you scientists, go away. When you've got the answer absolutely crisp, come back and tell us. But until then, please don't bother us. And what we know is that was the tactic, that was the strategy adopted by the cigarette companies when the evidence began to mount that smoking leads to cancer and all sorts of other serious health effects. And in this infamous memo, they said, aha, let's use normal scientific uncertainty, the things that scientists worry about a lot and the esteem of their colleagues depends on how well and honestly they talk about the errors. The first thing I was taught as a physicist at university is that no measurement is worth anything unless you say what the uncertainties, the error bars on. No number is valuable unless you know the uncertainties. So in order to maintain the esteem of my colleagues, I'm constantly trying to stay true to that principle. And the tobacco company said, that's great, because that uncertainty can be turned to our advantage, like jiu-jitsu, like the weight of your opponent. You flick them over. Doubt is our product. As long as there's doubt and uncertainty, we are offering people a way to get off this uncomfortable hook, to say, yeah, I don't like what you told me. I don't think you've really got it taped yet. It's very uncertain. Go away and tell me when you've got it sorted. So that's the first tactic. The second thing is to produce a lot of the stuff that says, there are cartoons all over the place of the guy wandering up and down the street with the end of the world is nigh. These people are just tapping into a particular, why do people go and see horror movies? Because they like to be sort of titillated by fear. And so these scientists are simply attempting to scare you to death. And of course, the reason they're doing it is that you'll give them money to kind of find out more and protect you. So it's a sort of scam. So these scientists are alarmists. And again, your reaction to go is, well, that could be true. And it does let me off the hook because I don't have to believe them anymore. Or maybe you can wave some emails around. Look at these scandalous emails. These people are really dishonest. You don't have to believe them at all. Even if they were dishonest, it doesn't mean that they're not right. Two things don't follow. But it's very easy, isn't it, to think, can't trust them, so I don't have to believe what they say. Now, what else can you do? This is the curve of global mean surface temperature over the last 150 years. So it's wobbling around. What I want you to look at is the last 50 years, the bit that's wobbling around. There's a lot of variation on it, natural variability of one sort or another, measurement uncertainty, but it's probably all real. So just in your mind's eye, draw a curve through that last bit of the graph. I'm not asking for chi-squared statistics, just in your mind's eye. Now let me just draw your attention to the last bit of it, which you may not have been focusing on, which has got that big spike and some other wobbles now. Take it away again. Now draw the line through it. Now how might I represent that if I had a particular ideological view? Well, I might do what the Daily Mail did and show you the last 16 years and say global warming stopped. Let's just go back and look at that. There it is. Is that a fair representation of what the data is showing? Personally, I don't think so. You have to make up your own mind. But if you want to believe that global warming isn't a problem, there it is. The Daily Mail tells you that, the Express tells you that, the Sun tells you that, the Daily Telegraph tells you that. Notice any pattern? The Global Warming Policy Foundation tells you that. This charity run by Lord Lawson, look at its logo. Its logo shows you the global mean surface temperature change this century. I couldn't possibly comment. But do you trust an organisation? Well. And what's going on here is, what's nicely framed in this picture. Peace for our time is what everybody wanted to hear, but it didn't happen. So again, what's going on inside your head? Nice little cartoon that... And what's important is not to focus on the uncertainties, but to focus on the risk. And this is where the business community is important, because business people and people who run organisations, if they're running them well, and we can talk about the financial services industry later if you like, but they are required by their boards and their trustees or whoever to have a risk register. And what they do is they think through all of the things, all of the unfortunate things that could happen to the organisation, and they consider what the probability is, and they consider what the impact is, and they multiply those two figures together, and they then sit down and demonstrate what they're doing to manage down the probability and the risk. Now, what we're talking about here are enormous risks, very uncertain, but they are non-zero. Now, people out there who say to you, look, it's very uncertain, this science. We should just sit back, do what humans have always done. We just sit back and we'll wait and see what happens, and then we'll fix it somehow. Well, there are two problems with this. Firstly, by the time you know, it's too late, because we are now experiencing the effect of energy imbalance that we set in the climate system 10, 20 years ago. And what we do today won't materially change the progress of the climate system for another 30 years. It's a very hard argument, actually, because what it says is if we all stopped emitting carbon tomorrow, there would be no measurable benefit for 20 years, and there would be no material benefit for 50 years. And, Groucho Marx said, why do I care about future generations? What have they ever done for me? And that's actually I was having this discussion with an economist the other day, and he said, that's a very good argument. But if we take both an ethical view and a practical view of risk, we should be managing stuff down. Now, how many people in this room do not have fire insurance on their house? One. Okay, two. All right. Well, that's interesting, and hopefully you've thought that through. But everybody else, all of the rest of you, including me, are paying good money, which we could spend on other things, to combat a 1 in 10,000 risk. I've talked to insurance people, and one of them told me it might be 1 in 100,000, but let's be generous, 1 in 10,000. So you think it's worthwhile investing money every year to be able to recover from the enormous consequences of an event which has a probability of 1 in 10,000. So if somebody is saying to you, I think we shouldn't take any insurance against climate change, they are in principle telling you that they think the probability of something nasty happening is much less than 1 in 10,000, because the nastiness that happens if the climate system shifts is actually a lot more damaging collectively than if your house burns down. And if you ask somebody to say, who has that position, how do you justify that? How have you come to that figure? They will not be able to give you an answer, because they cannot demonstrate that the likelihood that climate change will not be seriously damaging is less than 1 in 10,000, because it isn't. So thinking in terms of risk helps frame it in a way that leaves you in this position. You go, Jesus, well, we ought to be doing something about it, but what on earth can I do? I'm just me, can I do anything? Well, the answer is, actually, you probably can do a lot more than you think. We're all embedded in this carbon-based world. We shouldn't feel bad about it. It's not our fault, and it was unwitting, it was innocent, but we're beginning to live beyond our limits, and we just need to recognize that and think, well, okay, let's be sensible about this. What could we do collectively to address it? And there are at least 3 areas that we can work in. We can work in our personal lives. It turns out that when people actually calculate their carbon footprints, and there's plenty of, just go on the web and there are carbon calculators out there, it's pretty easy to reduce by 10% with no impact, no significant impact on your life at all. In fact, probably save you money. But some people who've thought about this find they can reduce their carbon footprints by a factor 2 and still lead perfectly happy lives. So in your personal life, you can not only control your own impact on the planet and not live beyond your means, but you can set an example and talk to others and discuss with others how we might do it more collectively. In your professional life, you can also have an influence. Now, when I was director of the Science Museum, it was relatively easy as director to say, we are going to reduce our carbon emissions. That was my privilege as director. But actually, wherever you are in the food chain of an organisation, you can be saying, I think it'd be more sensible if we didn't have all of these lights on. Looks like they're a bit unnecessary. There are lots of ways. Are these windows very good? I don't know. There are lots of things that you can do. Using paper is enormously carbon intensive. So rather than printing stuff out, why not just try and read it off your screen? So in your professional lives, there are many things that you can do. And what companies find when they do this, when they take a commitment, is that they save themselves money when they thought it was going to cost them money. You hear that all the time. And secondly, absenteeism, staff health, pride of being part of the company, all tend to go in a positive direction, because people feel proud of being part of an organisation that is taking an ethical view of the world, and also they know that there are limits to what they can do personally, so it makes them feel good that they're having a greater reach by being part of an organisation that takes this seriously. But then there's also the political side. Now, I briefed a House of Commons committee on climate change last year, and at the end of it, the 8 or 9 MPs present came up to me and said, what you have to understand, Chris, is that in the last year, we have not received a single letter or a single email from anybody in our constituencies about climate change. We've received mailbags about lots of other things, but nothing on climate change. And as long as that's true, don't expect us to be taking it very seriously. Don't expect us to put it very high on our agenda. So, you can calculate your individual carbon footprint and think of ways of reducing it, which really don't mean having to wear a hair shirt or not go on holiday. You can make choices. If you want to fly to the Caribbean, okay, you can either carbon offset, which I'm not very confident really works very much, but you could, if you like, earn up points, set yourself a target. Well, I'm going to bicycle to work for a few weeks, and then, that will offset the use of my carbon. You can manage it. But, it's not excruciating. Everybody fears they're going to lose something, but actually you can just manage it, and often you feel better as a result. You can, in your professional life, you can do things. Now, you can see me there and 1010, Franny Armstrong, who set up 1010, which was a few years ago, a commitment by organisations to reduce their carbon footprints by 10% in 2010, asked me as director of the Science Museum to commit the Science Museum to this aspiration. And be the first organisation to do so, to set an example. So I went to the facilities people at the Science Museum and said, 10% doesn't sound too bad, can we do that? And they shook their heads and sucked their pencils and said, we've just finished a 3-year investment programme in improving the windows and all the rest of it, and we've reduced things 17%, not sure that we can do another 10% this year, don't think it's safe. So I went and consulted with William Waldegrave, who is the chairman of the Board of Trustees, and we thought about it. And we came to a technical conclusion, which was, sod it, why don't we just commit to it anyway? So I went to the staff and said, I don't know how we're going to do this, we've signed up, we're going to have to do it, because we're going to look very bad if we don't. What are your ideas? And they came up with a brilliant set of ideas, and we reduced our carbon footprint by 24% that year. So there are things you can do in your professional life. And then the third example is the political. Now, some of you may remember that when the new administration came in, one of the things they tried to do was sell off the national forests, and there was a very strong reaction to that. And a small group of activists set up a website, 38 Degrees, where you could log on, and all you had to do was type in your postcode, and up came a letter to your MP saying, I really don't like this, and I'd like you to vote against it. Now, I'll tell you the figure in a minute. A large number of people signed the petition. 100,000 people sent email letters to their local MPs. I had 3 handwritten letters back from my MP who was actually explaining why she was not going to protect the forests. So I wouldn't have voted for her anyway, but you know, she completely lost my vote. But the point is that 538,000 people signed the petition. That's 0.7% of the British electorate, and it so frightened the government that they did an immediate U-turn. So when you think that your political clout, after all, we live in a democracy, it's your right to do this. So if you believe in this stuff, if you want to make a difference, you know, why haven't we all today written a letter to our MP saying, we're very worried about this, you know, we're not sure quite what can be done, but we would really like you to take this seriously so that we can have a sensible public discussion about it and figure out what the best course of action is. And I'm really pleased to say that at a talk I gave at the Diamond synchrotron facility a couple of weeks ago, I sort of went through this pitch, and I had a very nice letter from a lady a couple of days later saying, I was a real activist in my youth, but I've rather settled down in my old age, but I got so fired up by what you said, I wrote a letter to my MP saying that I really think they ought to take this seriously. It can have a big impact. So let me finish off. On the positive side, as director of the Science Museum, one thing I came away utterly convinced about is that human ingenuity is unbounded on an otherwise finite planet. And there are, of course, lots of new possibilities which allow us to connect to each other in ways that have not been available to humanity in the past. The bottom panel is the Facebook interconnections of the planet. I've forgotten 35 million, or was it 350 million users? I've forgotten the figure. But, you know, at present, that traffic is all about, you know, where I'm going clubbing tomorrow, or, you know, what celebrity I'm following on Twitter. However, we've seen with the Arab Spring, we just saw with the Italian elections, you know, 25% of the vote with the non-party, which organised itself through the internet. So we have powerful tools that allow us to do things that we haven't been able to do before. So I started this by saying this is a thriller. And it's got all the things in it. It's got bad guys, it's got good guys, it's got, you know, tantalizing fear, it's got, you know, all of the ingredients of a really killer thriller novel. But what we all want to know with that is what's on the last page. How does it turn out? And broadly, there are 4 possibilities, and I've got columns and rows here. The columns are human-induced climate change is not real. Sorry, Chris Rapley, you just got it wrong. You misinterpreted the data, and all your colleagues did. You know, the greenhouse effect doesn't work the way you thought it was. You know, whatever it was, some unknown is out there that will kick in and we'll all be saved. I wouldn't rely on it, but, you know, it could happen. Climate change is not real. Right-hand column, climate change is real, and in the extreme is really quite serious. It's a force multiplier. In a world that's full of stresses, and with people with nuclear weapons, you know, it could cause mayhem in the extreme. Probability very low, not 0, not 1 in 10,000 probably, but, you know, it could be a nasty outcome. And then across the rows, we take action, and both adaptation and mitigation, and maybe even geoengineering to give us a bit of time, or we don't take action. So let's go around the 4 squares. It's not real, and we take action. Well, we spend a lot of money. But actually, the companies who are looking at this and saying, where are we already seeing ourselves vulnerable to climate, the existing climate, the variability in the climate that we've got? Actually, investing a bit of money in making ourselves more resilient to that, not a bad thing. You know, in the end, it'll pay off on the bottom line. So when people say it's all unaffordable, it's not true. The more you think about it, the more there are ways that make it affordable and sensible. You may have to spend some money, but there's a cartoon which I haven't used which says, oh my God, we spent all of that money and made the world a better place for no good reason. So climate change is not real, and we don't take action. Well, it's a huge gamble, but we get away with it. We skate through. And of course, it's not what the banks ended up doing. They took a huge risk, and we'll see what happened in a second. Climate change is real and we take action. We get a gold star, we save the planet, we save humanity, the planet doesn't care, it's indifferent. But our children, our grandchildren, and the children of all other people manage to lead prosperous lives, living within their means and in some sort of balance with their planetary life support system. But the bottom right-hand corner is, of course, the bad ending to this thriller. Climate change is real and we don't take action. I love Apple Keynote. So, the end of the story has two bottom lines. One is that humanity is an unstoppable force of nature. That is, we're just like an asteroid impact. If you look at what we've done to biodiversity, we are that, aren't we? The sixth extinction. We are an unstoppable force of nature. It's unwitting, we didn't mean to do it, but we're doing it, and we're unstoppable. Is that what's going to happen to the climate system? Maybe. The other possibility is that we get our act together and we prove ourselves to be the ultimate smart species. And I think we'll know the answer within 20 years. That's my prediction. And that's where I finish. Thank you very much indeed.